Welcome to Unit 6, and we will be discussing thermochemistry. We did cover thermochemistry last year. Obviously, we're going to go into a little bit more depth this time. So I wanted to make a quick introduction video, give you an idea of what all we would be covering, and also just do some preliminary definitions and just to kind of get you started, okay? So thermochemistry is all about thermodynamics, and which is really just the study of energy and how it flows in and out of systems, how it converts from different types of energy back and forth as it flows. So energy is obviously really, really important. It's all around us. It's involved in the food that we eat. It helps heat our home. Coal and oil power manufacturing, transportation, everything that's involved in our industrialized civilization obviously is all about energy. And you can't really talk about energy in society without really considering fossil fuels. And as you know, fossil fuels are carbon-based. They are a finite source of fuel. In other words, at some point we will run out. And obviously that's a huge concern if you were to ever look at, say, graphs of energy consumption over time in the US or for the world for that matter. You're going to see just huge changes. And as our country grows into industrialized processes, obviously that consumption goes up just in an amazing rate. So obviously we're dangerously dependent on oil and other fossil fuels, and it's really important to know that at some point we need to find alternatives. And because this is so important, I think it's really also important to understand the process of energy flow, what produces it, how we can produce it, and understand it on a microscopic scale as well as a macroscopic scale. Which brings us to chemical energy in general. So you can think of it as chemical energy in a living cell, perhaps, how it has its own little chemical factory, that it can power its systems by this little these chemical reactions, like cellular respiration in particular. There's actually, and I read an article not too long ago about a company that was trying to make the idea, the chemical reactions in cellular respiration on a commercial level to see if they could actually come up with some way to make that on a macroscopic scale. It was pretty interesting. But obviously a conversion from energy from one form to another, whether it's macroscopic in terms of conversions in maybe a pendulum, or on a microscopic scale when energy is stored as sugars or something like that, really the processes have the same principles. And so it's important to understand the microscopic version as well. So the objectives we're going to cover, and the first one here I'm going to cover for the most part in this video, we're going to talk about heat, work, internal energies, just some of the basics. Moving forward, we'll talk about thermochemical data in terms of enthalpy in chemical reactions. We will do some Hess's Law, if you remember those. We did do some of those last year. They're going to be a little bit more complicated this year. We'll do some calorimetry, which is those QSMAP problems we did. We'll talk about energy change, entropy change, and general flow in terms of spontaneity. So this is towards the end there. One thing to mention here, I think it's important, this unit 6 in AP Chem, is actually 2 chapters in the book. It is chapter 6 and chapter 17. So we will be covering quite a bit of information in here. Now, the last part of chapter 17 is about equilibrium, which we have not covered yet. We will include that later on, towards the beginning of the year, actually. All right, so let's just cover some basics here. Energy is defined as the capacity or ability to do work or produce heat. And obviously we're going to concentrate specifically on heat transfer in terms of endothermic and exothermic chemical processes. Obviously energy can also be classified as potential or kinetic, as you well know. Potential energy is due to position or composition, and I'm sure you can think of many, many examples, not just a water flowing behind a dam and running through the turbines, but maybe the diver on the diving board as they leap, and then turning into kinetic energy. But it can also be on a microscopic scale. It could be attractive or repulsive forces. And you can think of this as maybe attraction between two ions. I have a cation and an anion. And as they're attracted to each other, they would move towards each other. So that potential of them staying apart, that would be potential energy holding them apart. But as they are attracted to each other, then that potential turns into kinetic as they move together between the two. So kinetic energy is obviously based on motion, and it's if you look at the equation, it's the mass of the object in kilograms times the velocity squared. And actually, if you look at this right here, the mass times velocity squared is the definition of a joule. So a joule is equal to a kilogram times a meter squared over, divided by seconds squared. That's what a joule is. So kinetic energy is typically measured in joules. So the law of conservation of energy just tells us that energy can be converted from one form to another, but obviously we can't create it and we can't destroy it. And the energy in the universe is constant. So this idea of the law of conservation of energy is also called the first law of thermodynamics. So this idea of conversion of energy, the book actually just gave us a little diagram about conversion of energy. And so they have this little spot or this ball here that's being held into place up here. And it has lots of potential energy because it's held up higher than the other, right, due to gravitational pull. And so as this guy, this potential energy in A, once we let go, this A, potential energy in A turns into kinetic as it flows down, and it bumps B, and then so B then acquires A's kinetic energy through this transfer. And then if you look, then B ends up higher in terms of position, so it has gained potential energy. So what potential energy was originally in A is now held by B, minus a little bit of friction and or energy loss to the surroundings. Which brings us to something called work. So work is a force acting over a distance, and it can transfer energy. So again, this idea that it took work to get B from here to up here onto this hill, right, to change its position. And so the energy originally stored in A was transferred to B through work, and this work then took B up to a higher position. So work acts as this force, the force from A transferring the energy to B. Another thing to clarify would be the difference between heat and temperature. A lot of people use the words heat and temperature as if they are the same thing, and they are very, very different. Temperature is an actual property. It's a physical property. And so when you take a thermometer and you take a temperature reading of an object, say maybe you put it in a solution in a beaker, what it's actually doing is measuring the kinetic energy. It's measuring that random motion of the particles in that substance and putting it in something quantifiable that we would call temperature. Now heat, though, heat is not a property. It's just a transfer of energy. And so it's also quantifiable because we can take the temperature reading before and after the energy is transferred. So we can quantify it, but it's not a substance, it's not a property, it's just a transfer of energy. So this brings us to something we did not discuss last year, really, and that is the idea of pathway. And so when we talk about the transfer of energy via work and heat, it depends on specific conditions called a pathway. Okay, so energy change is independent of the pathway. This is really important to put here. Independent of the pathway. What they mean is the change between what you start with, whatever substance you start with, and the energy change between that and the final product is going to be the same no matter how you get there. You could have 3 chemical reactions that take you from your starting point to your ending point. Or maybe you could have 7 chemical reactions. But the idea and the energy of what you started with and the energy with what you ended with will always be the same. It'll only be the same difference. I didn't say that very well. But the change in energy will be the same no matter how many different chemical reactions it took you to get there. I hope that helps. The book goes into a little bit more detail. And we will be talking about this again in this unit as well, but this is at least an introduction. Work and heat, on the other hand, are dependent of the pathway. So it does matter. Energy transfer between what you start with what you end with. The work, if you did 3 chemical reactions to get to your final product versus 6, the work in between that is definitely dependent on how many you do. Heat also transferred is the same thing. It depends on how many different ways you take to get to the final product. Again, I hope that makes some sense, but we'll keep working on it. And there's another analogy as well. So if we're talking about pathway, we're also talking about a state function. So by definition, a state function or state property refers to a property of a system that depends only on its present state. So in other words, if something is pathway independent, it is a state function. Okay? In other words, it doesn't matter how you got there, you're going to have the same change in energy from where you started to where you ended. Okay? That would say energy is a state function. Okay? A change in function is going from one state to another state is independent of the particular pathway. That makes it a state function. So down here at the bottom, to summarize and make sure you have this written down somewhere, energy is a state function. It does not matter the pathway in which you took to get from beginning to end. Work and heat are not state functions. They are pathway dependent. So here's my analogy I really hope helps. So let's say you're traveling from Chicago and just happens to have an elevation of 674 feet to Denver, which is over 5,000 feet elevation. The change in elevation is always going to be 5,000 minus 674 for 4,600 feet, regardless of whatever route you take between those two cities. You could go through Texas, and the elevation change from Chicago to Denver is going to be the same no matter if you went through Columbus or Texas or Wyoming. It doesn't matter. The change is still the same. That's what I'm talking about in terms of energy. Okay? Energy is a state function. It doesn't matter how you got there. This elevation change is the analogy between this and energy change. Okay? It won't matter between the two. Okay? Now, the distance traveled depends on how you made the trip, right? That's more like work or heat. That is dependent on the pathway. So in this analogy, elevation is a function that does not depend on the route and therefore is a state function. Okay? Elevation is a state function. Okay? Distance is not. Distance depends on how you got there. If you went to Houston first, right? So back to this idea of chemical energy. When we talk about energy, we're talking about chemical reactions, and we can divide things into 2 parts. If we're talking about the system, okay, we're typically talking about the chemical reaction itself, okay, the reactants and the products. The surroundings are everything else, right? Everything else around the system. In a chemical reaction, the surroundings could be the container. They could be the water in the container. They could be the room, or anything else you can think of. But we're going to split them up into those 2 parts to talk about energy flow. So, speaking of energy flow, and we're almost done here, exothermic. When a reaction evolves heat, it is said to be exothermic. So the energy is flowing out of the system. And you can think of it as heat or energy as a product. It is at the end of the reaction. It's on the right side of the reaction. Endothermic, on the other hand, is just the opposite. It absorbs energy from the surroundings. And so it's said to be endothermic. Energy flow is into the system from the surroundings. And so that way, energy and heat would be a reactant. So if you think about it, where does that energy go if we have an exothermic reaction? Well, if it's going to the surroundings, then it's released as heat, which remember is just a transfer of energy. And then that turns into kinetic energy in the surroundings. So we interpret an exothermic reaction as getting hot because the potential energy in the reactants turned into kinetic energy for the surroundings. Let me say that again. An exothermic reaction took the potential energies of the reactants and eventually turned it into kinetic energy in the surroundings. That is why we end up feeling the heat in an exothermic reaction. And it is the difference specifically between the potential energies of the reactants and the products. So total energy is conserved. So the energy gained by the surroundings is equal to the energy lost by the system. Okay? So potential energy going into kinetic, not unlike your pendulum, right? Has potential energy, and as it swings down, it gains kinetic energy. It is the same idea, microscopic, the microscopic version, okay? So this always holds true. Any exothermic reaction, some of the potential energy stored in the chemical bonds is being converted to thermal energy or random kinetic energy via heat. Okay. I know I've showed this to you once before, but if, as an example, methane and O2 in combustion as reactants have lots of potential energy, and as products, CO2 and water, this change in potential energy is what goes out to the surroundings and becomes kinetic energy and heat. In an exothermic process, the bonds in the products are stronger than those of the reactants. So let me go back up here. These down here are more stable. Their bonds are stronger than my reactants. Their potential energy was much, much higher. So more energy is released by forming the new bonds in the products than is consumed to break the bonds in the reactants. So again, looking at this has less potential energy, this has more, and it took less energy to break these as we did, it took less energy to break these than the energy it took to, sorry, I'm not saying this correctly. Let me go back over here, see if I can do this better. Sorry about that. So more energy is released by forming the new bonds in the products than is consumed to break the reactants. My bad. So remember, when we form something, we get energy back, right? And when we break things apart, that takes energy. So the idea was it didn't take as much energy to break these apart. And we didn't have to spend that much energy, we didn't spend any energy forming these guys. We got that energy back, lots and lots of it. All right. Now for an endothermic, and this will be wrapping this up. In an endothermic reaction, energy flows into the system as heat and is used to increase the potential energy of the system. So therefore, the products have a higher potential energy and weaker bonds than the reactants do. So complete opposite of what we saw before. And of course, this can be quantified. And this is going to be a new equation for you. The internal energy of a system is the sum of the kinetic and potential energies of all the particles. Hopefully that makes sense. If we can break energy into potential and kinetic, we can add those up and get the overall energy. So internal energy, we're going to just, it's shown here as delta E equals Q plus W. Change in E is the change in internal systems energy. And we also have Q is heat. If you remember Q-SMAT from last year, Q is heat and W is work. So in thermodynamics, if you remember, there's always two parts to all of our answers. There's how big there was of it, or how big the change is in energy, right? The magnitude of it. And then it's the sign. And positive and negative, you can't really think of it as the mathematical sign in thermodynamics. You have to think of it as which direction is the energy going. And when you determine that, I always suggest that you take on the point of view of the system. Is energy coming into the system or is it going out of the system? So as energy is going in, let me go back to that. As energy is coming into the system, that's positive, and as it's leaving, if you remember, I used to say it was like cash flow. Comes in, it's positive. As it leaves, it's negative. So in an endothermic process, we actually have energy flowing into the system, and the system's energy is increasing, either through heat or through work. Okay, so the surroundings lose kinetic energy, because that kinetic energy, those random movements in the particles of the surroundings, actually go into the products. Okay, right here, all this energy went into the potential energy of the products, raising their potential energy. They're less stable. Their bonds are weaker. Okay, so in other words, it didn't take as much energy. It took a lot of energy to break these apart and form these. So we raised the potential energy there. In an exothermic process, energy flows out of the system, and the overall system's energy is decreasing. Right? So we talked about that. We have high potential products, and then high potential reactants, low potential products, and the difference is released into the surroundings. So hopefully you see that difference there. Okay. I'll do a quick example problem. I hope that you see that this is pretty straightforward. Q plus W is change in E. Calculate the E for the system undergoing an endothermic process in which 15.6 kilojoules of heat flow and 1.4 kilojoules of work is done on the system. So the key here is really about sign. Endothermic is your hint, which means Q is positive because it's going into the system. The work is done on the system. So the work is going into the system as well. Both are positive, and then you add them together. So the hardest part on this is really just determining sign. They're pretty straightforward. Excuse me. So there's only one other idea that I want to talk about in work, and it's really done with gases. And I tell you what, I think this video, we've gone far enough. So let's just end on that, and we'll talk about work in class. So I hope you have a good rest of the day, and I will see you tomorrow.